Hello viewers, in today's session we are going to discuss an important problem from functions, right? And here we are given this problem in which we have to show that this function f of x, which is equal to 2 times tan inverse of e raised to 10x minus pi by 2, where x belongs to the set of real numbers, is an odd function, right? So first we have to show that this function is an odd function, and then we have to find the intervals in which this function f of x is an increasing function, right? So first we'll see this function is an odd function, and then we'll find out the interval in which this function f of x is an increasing function. So let us start. So now we have f of x is equal to 2 times tan inverse e raised to 10x minus pi by 2, where x belongs to the set of real numbers. So now here to show that this function is an odd function, let us replace this x by minus x, right? So what we will get, we'll get f of minus x is equal to 2 times tan inverse e raised to minus 10x, and here we have minus pi by 2, right? To show that the function f of x is an odd function, first we'll replace this x by negative x, then we have to arrive at this result, that is f of minus x is equal to a negative of f of x, right? So now we have this expression for f of minus x. Now see, here we can now write 2 times tan inverse 1 over e raised to 10x minus pi by 2, right? So e raised to minus 10x can be written like this, 1 over e raised to 10x, because we know that e raised to minus mx is equal to 1 over e raised to mx, right? So here we have to now make use of an important identity from inverse trigonometric functions, right? So we know that the cot inverse of say theta is equal to tan inverse of 1 over theta. So this is an important identity from inverse trigonometric functions. So cot inverse theta is equal to tan inverse 1 over theta. So here our theta is equal to e raised to 10x, right? So theta can be taken as e raised to 10x. So now we have 2 times tan inverse, and we have 1 over theta minus pi by 2, right? So we can now write 2 times tan inverse 1 over theta can be written as cot inverse theta minus pi by 2, right? So now here we can again make use of an important identity from inverse trigonometric functions connecting tan inverse theta and cot inverse theta. That is tan inverse theta plus cot inverse theta is equal to pi by 2, right? So cot inverse theta can be written as pi by 2 minus tan inverse theta. So here we can now write 2 times cot inverse theta can be written as pi by 2 minus tan inverse theta and minus pi by 2, and remember theta is equal to e raised to 10x, right? So now multiplying these two terms by 2, we have here simply pi by 2, or we can simply write pi because 2 and 2 get cancelled. So here we have simply pi minus 2 times tan inverse theta minus pi by 2. So now pi minus pi by 2 is equal to pi by 2. So here we have pi by 2 minus 2 times tan inverse theta, Now taking negative sign common here, we have minus 2 times tan inverse theta minus pi by 2, and theta can be replaced by e raised to 10x. So now we have f of minus x is equal to a negative of 2 times tan inverse theta minus pi by 2, and if we now replace theta by e raised to 10x, we have 2 times tan inverse e raised to 10x minus pi by 2, and this expression is equal to our original function, that is f of x. So we have a minus f of x, right? So we have reached the condition, that is f of minus x is equal to minus of f of x, which is the condition for a function f of x to be an odd function, right? So this is how we can prove that this function f of x is an odd function, right? Now let us see the interval in which this function f of x is an increasing function. So now let us differentiate f of x with respect to x. So d by dx of f of x is equal to f prime of x, that is d by dx of 2 times tan inverse e raised to 10x, and here we have minus pi by 2, right? So the derivative of tan inverse e raised to 10x is given by 1 over 1 plus e raised to 10x square, and then by chain rule we have to find the derivative of e raised to 10x, and the derivative of pi by 2 is 0, right? So here we have used an important result, that is d by dx of tan inverse of x is equal to 1 over 1 plus x square, right? So taking this entire term, that is e raised to 10x as x, we have 1 plus x square, so x is e raised to 10x, so we have e raised to 10x square, and then by chain rule we have to find the derivative of e raised to 10x, right? So we have 2 times 1 over 1 plus e raised to 20x, 2 times 10 is 20, and then the derivative of e raised to 10x is 10 e raised to 10x. So now we have 2 times 10 is 20 e raised to 10x, and here we have 1 plus e raised to 20x, right? So the derivative f prime of x is equal to 20 times e raised to 10x divided by 1 plus e raised to 20x. So now consider this term, right? Now see, e raised to 10x is always going to be greater than 0 for all x belonging to the set of real numbers, right? So e raised to 10x is always a positive quantity, so 1 plus e raised to 20x is a positive quantity, right? So it implies that this entire term is greater than 0 for all values of x belonging to the set of real numbers. So now this entire term is greater than 0. So we can easily conclude that f prime of x is greater than 0 for all x belonging to the set of real numbers. And this is the condition for a function f of x to be strictly increasing, right? So our function, this function, that is f of x, is a strictly increasing function for all values of x belonging to the set of real numbers, because f prime of x is always greater than 0 for all values of x belonging to this interval, right? So this function f of x is a strictly increasing function in the interval that is from minus infinity to plus infinity, which can also be written as f of x is strictly increasing for all values of x belonging to the set of real numbers, right? So viewers, this is how we can solve these kind of problems.